Welcome to the video on logarithms and graphing logarithmic functions. Logarithms really are a part of your everyday life. If you ever have heard about an earthquake anywhere, the Richter scale is based on a logarithmic scale, or tornadoes, the category 1, 2, 3, 4, or Fujita scale is also based on logarithms, as well as hurricanes. So nature is full of logarithmic scales. As a little aside, just because it's interesting, the word logarithm comes from the Greek, and logos means ratio, and arithmos means number. So do with that whatever you want. The definition of a logarithm is an exponent, or power, to which a base number, such as 10, must be raised to produce a given number. So just for your sake, you should really think of a logarithm as just an exponent. Here's an example. We're used to exponential notation. Say I had 3 to the power of 2. Well, you know that is 9, right? So what logarithms do is kind of reverse the process and say, in a way, 3 to what power is 9? So the answer would be 2. So we would call 2 the logarithm of 9. But the base number is 3, so we need to notate that somehow. And so we would say log base 3 of 9 is, and we know the answer is 2. So that's what the logarithm looks like. This is what the exponent or exponential version looks like. So 3 to the power of 2 equals 9. Therefore, log base 3 of 9 equals 2. And you're going to want to let that sink in a little bit, and we'll do plenty of practice with it, so it will come eventually. Don't panic. Down here we have the official definition of a logarithm. This is how it is written in logarithmic form, and here is how we could write the same idea but in exponential form. Remember, it is read log base b of y is x. Okay, so let's practice with our new form called logarithmic form and write these logs as exponents. Our first example says log base 2 of 8 equals 3, and you already have probably some sense of how we need to write that. The base number comes first for exponential form, then the exponent of 3, and we know that that equals 8, which is sometimes often called the argument. So 8 is the argument. Here we have log base 4 of 1 equals 0. Switching that into exponential form, we would write 4 to the power of 0 equals 1. Log base 12 of 12 equals 1. That would be written 12 to the power of 1 equals 12. And log base 1/4 of 4 equals negative 1. Don't panic, just follow the form. Your base number is 1/4. Your exponent is the negative 1. And that truly does equal 4, and you know that because of your exponent rules. So down below you have your guided practice. Pause the video and come back when you're done. All right, here are your answers. How did you do? Now we're going to evaluate logarithms now that we know kind of what they are. And if we look at our first example, we are asked to find log base 4 of 64. What the question is really asking is 4 to what power gives you 64, as it says right here. Sometimes people like to turn these back into exponential form to help them answer the question. You don't have to, but it is a technique. So what you're really thinking of is 4 to what power gives you 64. Now when I assess you on this, I don't want to see you answering it like this. This exponential form only helps you get to the answer. I want you to answer it in logarithmic form. So log base 4 of 64 is the power in which 4 is taken to in order to get 64. So what power is that? That equals the power of 4. All right, the next example is log base 5 of 2/10 equals what? So we are looking for this answer up here. Again, you can reverse it in your head. 5 to what power would give you 2/10? So think about it, because we can write 2/10 in a different way. I mean, you could write it as 2/10, but that would reduce to 1/5. So the question is, how do I get that 5 in the denominator? Hopefully you remember your exponent rules, because a -1 up there would give you 1/5. So log base 5 of 2/10 equals a -1. Letter C, log base 1/5 of 125 equals what? And so you have 1/5 to some power gives you 125. Well, you see that your 5 is switched to the numerator, so you know that your answer needs to be a negative exponent. And what number would that be? That would be 3. And you can use your little blue cheat sheets to help you answer these questions. Otherwise, your calculator does a nice job too. So let me rewrite that nicer. It is equals a -3. Letter D, log base 36 of 6 equals what? Be careful with these. They can get tricky if you're not thinking about them properly. It's saying 36 to what power is 6? Well, you know, if I square rooted 36, I would get 6. And as we write that as an exponent, that would be the power of 1/2. Okay, I'd like you to flip the paper over and do the guided practice problems on the next page. I can't do it on the video here, or I would lose my spot. So you're doing guided practice problem number 5. It starts off log base 2 of 32 is what? And I want you to do number 5 and 6. Pause the video and come back when you're done. All right, log base 2 of 32, you should have 5 down for your answer. And log base 27 of 3 is 1/3. All right, two definitions that we need to learn about. One is common log and one is natural log. By the way, I keep saying log because that's just the shortcut of saying logarithm. A common log is a logarithm with base 10. So I will write that down. And we have a base 10 number system, so that's why they call it a common logarithm. And when we write the common log, we either write log base 10 of some argument, or we're more commonly write log with no base written. So if you see no base number down here, you are to assume that it is log base 10. And you will see it like this most often. Okay, next we have a natural logarithm. This is a cool kind of thing that we're going to talk about. Well, we talked about it a little bit when we talked about the natural number e. So we have a natural logarithm. So that would be a logarithm with base e. And we write that simply as log base e, or more commonly, you'll see it like this, ln. And that is implying that you do have a natural log base e there. So ln, and it doesn't have to be cursive, it can be printed. So ln is the natural log base e. All right, everybody loves to practice with their calculators, so get your calculators out because we're going to use them to evaluate logarithms. Thank goodness. Unfortunately, up till now, we can only evaluate logs that are natural bases or base 10s, but your calculator can do that much. We will deal with using our calculator to evaluate logs with different bases toward the end of the chapter. So let's look at the first expression. It is log of 8. Now, because there is no base number written, you are to assume that's log base 10 of 8. And so if you have your TI calculator, all you have to do is hit the log button, and that is found just to the left of the number 7. It's written in white, so it is the first command key. So it's LOG. So just hit log and then type in 8 and hit enter, and you will get your answer, which is 0.90308. So I'll just write down what your display shows, and it keeps going on. So we'll just round or do our little dots and 0.903 dot dot dot. And a cool thing to do is to actually take 10 to the power of that number. Don't clear it out, leave it on there. Just do 10 and then use your caret key to the power of second answer if you wanted to, and you will see that you get that 8 right back if you use this. So it's about right on to 8 as long as you didn't round. Alright, the natural log button is right below the log button, so to the left of the 4. So just hit ln of 0.3 and hit enter, and you get negative 1.2 something, 1.20 dot dot dot. And again, if you wanted to check that argument of 0.3 comes out, it's kind of fun. So take e, which you're going to need to use your second key, e to the power of, I'll write it down actually, e to the power of negative 1.2 dot dot dot. That just means leave the answer in your calculator, and you will get 0.3 back out. So it's just nice to check your answers sometimes. Okay, let's look at example 4, where we actually are going to evaluate a logarithmic model, and it's about tornadoes. It says the wind speed S near the center of a tornado is modeled by this equation given here, and they're telling you d is the distance that the tornado travels. In 1925, a tornado traveled 220 miles through 3 states. Just think about that for a second. Wow. We're supposed to estimate the wind speed near the tornado's center. So the distance was given to us, and it is 220 miles. So that d right there is going to get substituted with the 220, and we will evaluate this equation. So log 220, so we assume the base is 10, plus 65. Now all we're going to do here is solve this, and in order to do that, we're going to need our calculator. And so you can just plug that right in your calculator. Do 93 times log 220 plus 65. And you should get something like 93, and the log of 220 was 2.342. That's what I got. Plus 64. And so your final solution for what the wind speed was near the center of the tornado was 282.8 miles per hour. That's fast. Destruction. All right. Let's have you go back up to the top and do the guided practice problems that, oh, I already did the answers for you. Oh, wait, that's not them. They're on the next page. Never mind. All right, for guided practice number 7 and 8, why don't you whip those out real quick on your calculator just to make sure we're all getting the same answer. Pause the video. And there are those answers. All right, there are 4 properties that I want to go through right now. The first 2 are just normal, and then the next 2 I like to give them a name. I call them the cancellation properties. So the first properties are just basic properties of logarithms. Just like we had properties of exponents, we can have properties of logarithms. So the first one is kind of generic. It says log base b of 1 equals 0. That's actually a property. But it really kind of makes sense, because if you reversed it into exponential form, all it's saying is b to the power of 0 equals 1. And we know that anything to the power of 0 is 1. So log base b of 1 equals 0. Anytime you see 1 for an argument, you're using this property. The next property is kind of common sense too, where if you have log base b and your argument matches it, well, that means that exponent of the base b had to be 1. And again, this comes from the exponential idea that b to the power of 1 is b. So keep those 2 in mind. The next 2 seem a little more complicated. I can explain to you why they work, but I'm just going to write them down to begin with. The first one is log base b, and then this one's kind of weird because your argument b is going to have its own exponent x. And this, maybe you can see it already, is going to equal x. The fourth property I want you to think about is if you had a base number b and it had an exponent with a log in it, these can get weird, an exponent with a log in it, that answer is going to be x. And I'm going to show you back in exponential form why these make sense. So let's go back to number 3, and I'll give you an example. If I had log base 2, so I'm just copying this form here, log base b, and I'm using numbers, log base 2, and I told you that the exponent of it was 3, then you should already know that this argument, because 2 to the power of 3 is 8, really, that I could have written this as 2 to the power of 3. So look how those match each other. Log base b of b to the power of x equals x. So log base 2 of 2 to the power of 3 equals 3. And this is why I like to use the idea of cancellation property, because what's really kind of happening is this log base 2 in that argument are in a way canceling, leaving you with that 3. They kind of undo each other in a way. The fourth property there, b to the power of log base b of x equals x. And these are telling you always what they're going to equal. So if you see something of this form, your answer will be whatever number is there. And if you see something of this form, your answer will be whatever number is there. So using a real life example, let's say I have a number 2 that is my base number, and I put log base 2 of 8 here. Well, what does that really mean? What is the log base 2 of 8? What is the exponent where you take 2 to the power of it to get 8? Well, that answer, you know, is 3. So I could really replace this whole thing with the power of 3, because that's what this is. And then you should know that 2 to the power of 3 is in fact 8. So again, that's why I call it kind of the cancellation property. It's a property, they're undoing each other in a way. And so if you ever see anything in this form where you have the base number and a log to the same base, that these things kind of in a way cancel each other out, and you can just write down the number that existed up in the argument or the exponent's argument. All right, the next thing we need to talk about is the idea of inverse functions. And I've mentioned this before. When I talk about a logarithm, I say it's just the inverse of an exponent. Remember in the past when we would check to see if two functions were inverses, that I told you the key was to take g of f of x, just look at this part right here, g of f of x, and if that equaled x, that meant the two functions were inverses of each other. And then you also had to take f of g of x. And if that composite led you to a final number of x, that you knew for sure that the two were inverses of each other. So look at what we have here. They're telling you that g of x is log base b of x. Well, if I took g of f of x, which means I take b of x and substitute it in here, you can see right here that's your substituted f of x, that you do indeed get the value x because of that cancellation property that we talked about up here. F of g of x works sort of the same way. I take g of x, which is log base b of x, and substitute it in f of x up here. And you can see again, because of that property I called the cancellation property, that you get x. So log base b of x and b of x are inverses of each other. So that is just another property that we need to think about, the inverse property. But let's actually use it. Let's go down here and look at the idea of the inverse property with this example, where it says you have the base 10 taken to the power of log base 10 of 4. So we're really using that property again, where well, which property was it exactly? It was this one right here, number 4. And so I want you to think of these as canceling each other. And your final answer when you evaluate it would just be 4. So 10 to the power of log base 10 of 4 equals just that number 4. All right, the next example is log base 5 of 25 to the power of x. Now this one you're going to see quite often. It has a log base 5 and it has this argument of 25. And gosh, if only this had a base of 5, then I could use this property up here to cancel things out. Well, you are well within your right to actually change this number here to a base number of 5. I'm just rewriting the same number. So I would write this as log base 5 of, and instead of writing 25, I'm going to write 5 to the power of 2. Now that x is still there, and it's just going to hang out up there in the exponent with 2. And so notice all I did was rewrite something using a different number here, 5 to the power of 2. But these are identical and equivalent right now. So go back to that cancellation property number 3 and realize that log base 5 and the argument there 5 are going to undo each other or cancel each other, and you will end up with a final answer of 2x. I understand that this can be weird and very uncomfortable, but trust me, you will get good at it because we're going to work with them a lot. Alright, let's find some inverse functions. We know how to use the properties, but let's actually find them now. So down here in letter A, it has y equals 6x, and it wants us to find the inverse function. Well, this is where you're going to need to use these definitions up here, so make sure you don't forget about these. I already told you that log base b of x is the inverse of b to the x. Well, look at what this is right here. This is, your b is 6, so this is 6 to the power of x. So your log is going to look, or I'm sorry, your inverse is going to look like that function right there. And so we would write log equals, and again, I'm looking right up here because these two are inverses of each other, so I'm just going to write log base 6 of x. Not much to think about there, but you do have to remember your definition of a logarithm inverse. Alright, let's look at letter B. That one is trickier because now we're moving into natural logs. And so this goes back to things you've done before, finding inverses. This one might be a little more straightforward. You're not using that definition, where you just switch your x and y values and solve for the y. So I have y equals natural log of x plus 3. So our first step always was to switch the x and y. So I'll write switch x and y for your notes. And you would end up with an equation that looks like x equals natural log of y plus 3. Alright, so now what I'm going to do is I'm going to get this thing out of logarithm form and back into exponential form. To help you see it, I'm going to write this. Instead of using ln, I'm going to use log base e, because that's what it is. And the inverse of it would be the exponential form of it. That helps me solve it for y. So remember how to convert between logarithms and exponents. I'm going to take the base number. Think about it for a second. What is the base number of this log? The base number is e. And e, what is the exponent of this log written right here? Which number is the exponent? And by the definition of logarithm, the exponent is that x. So far I'm just converting it back into exponential form. So e to the power of x equals what? Well, it's going to equal the argument of that logarithm, which is this whole thing, y plus 3. So I'll write that on the right side. So now I have e to the power of x equals y plus 3. And again, all I did was convert it out of logarithmic form into exponential form. But you need to solve for y. You're not quite done, and so I would subtract 3 from both sides. So e to the power of x minus 3, let me erase that, minus 3, I'm trying to write now, minus 3 will equal y. And you've solved for y. So these two functions are indeed inverses of each other. And feel free to take f of g of x and g of f of x and see that they're both going to equal x, which was the key. We are going to save graphing logarithms for another day.